Imagine you're holding a solar panel. It looks pretty simple. Light hits it and electricity comes out. But underneath that simplicity is pure quantum mechanics. At its core, solar energy conversion begins with something surprisingly minimal, a two-level quantum system. But what does that even mean? Let's zoom in. Inside a solar cell, typically made of silicon, electrons occupy specific energy states. Quantum mechanics tells us that these states are discrete. Basically, there's no in-between. So, it either occupies a lower energy state, the ground state, or a higher one, an excited state. And that's what we call a two-level system. Now, let's introduce some sunlight. Sunlight consists of photons, which are called packets of energy, described by Max Planck and later formalized in quantum theory. Each photon carries energy proportional to its frequency, where E equals hf. When a photon with exactly the right energy hits a material, something remarkable happens. The electron absorbs the photon and transitions from the lower energy state to the higher one. Not gradually, not partially, but instantly. This is what we call a quantum jump. Mathematically, the probability of that transition can be described using the time-dependent quantum mechanics. In an idealized two-level model, the electron's excitation probability oscillates in time, and this is what physicists call Rabi oscillations. But there's a bit of an issue. In real solar cells, we don't want oscillations, we want charge separations, so we can get more electricity. So, engineers design materials with built-in electric fields, typically at a p-n junction, that immediately pulls the excited electron away from its original state. This prevents recombination and allows current to flow through an external circuit. That flow of electrons, that is electricity. So fundamentally, solar energy conversion is not really just light hitting a panel. It's a quantum interaction, a photon matching an energy gap, an electron making a discrete transition, and a system which is engineered to extract that excitation before it relaxes. The two-level quantum model doesn't capture every complexity. Real semiconductors have bands, photon interactions, recombination mechanisms, and way more. But it captures the core mechanism, energy absorption as a quantized transition. And that's the beauty of it. At the heart of every solar farm, rooftop panel, every satellite powered by sunlight, it's a single quantum event, repeated billions of times per second. If you guys enjoyed this video, make sure to like and subscribe. Be curious like a child, the world needs more of it. Bye!